Hello students, in today's lecture we are going to learn about electric charges and fields, and this is theory part. Disclaimer: the images, text and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the same. So in today's lecture, we will cover first is introduction, electric charge, conductors and insulators, basic properties of electric charge. Then we will learn additivity of charges, conservation of charge. Then we will learn quantization of charge. Then Coulomb's law. And the remaining topics we will learn in upcoming lectures. Electric charges and fields. So here question arises, what is electrostatics? So electrostatics deals with electric charges at rest. Static means not moving. So we study charges that are stationary. And what is electric charge? Electric charge is a basic property of matter, just like mass. It causes particles to experience a force when near other charges. So some common experiences of static electricity include sparks and crackle sound when removing synthetic cloths or sweaters, specifically in dry weather. In dry weather, when you removing synthetic cloths or sweaters, you hear sparks or crackles. This phenomena happens due to charge. Lightning during thunderstorms. Electric shock sensation when opening car doors or touching bus handle bars after sliding from seats. When you slide from the seat, you acquire negative charge. And when opening car doors or touching bus handle, you feel like a shock. The cause behind these phenomena is the discharge of accumulated electric charges through our body. The cause is discharge of accumulated electric charge. These charges accumulate due to rubbing between insulating surfaces, generating what we call static electricity. I hope this is clear. Static refers to things that remain stationary or don't change with time. What is the meaning of static? Remain stationary, don't move with time, or we can say don't change with time, is known as static. The study of forces, fields and potentials that arise from static charges falls under electrostatics. These everyday observations demonstrate how static electric charges affect our daily lives through various forms of discharge, particularly when insulating surfaces interact through rubbing, leading to charge accumulation and subsequent discharge through conducting paths. So these are the common experiences of electricity, or we can say static electricity. I hope this is clear. Electric charge. Like charges repel and unlike charges attract each other. The discovery of amber's ability to attract light objects when rubbed with wool or silk cloth is credited to Thales of Miletus, Greece around 600 BC. The term electricity comes from the Greek word that is electron, meaning amber. Multiple materials pairs were known to attract light objects. If a body have charged, then they attract light objects like straw, pith balls, and paper bits when rubbed together. Experiments showed that glass rods rubbed with wool or silk repel to each other. Look at here. This is glass rod. When rubbed with silk thread, they acquire charges. However, the glass rod attracts the wool. Similarly, plastic rods rubbed with cat's fur repel each other but attract to fur. The plastic rod attracts the glass rod but repels the silk or wool used to rub the glass rod, while the glass rod repels the fur. So the main thing here is this: suppose we have two charges and both are like charges, then, or we can say in that case, they are repelled to each other. Suppose we have a glass rod, the charges is positive. Similarly, another glass rod charges is positive. When both glass rod comes to contact with each other, then they are repelled to each other because they are like charges. If we have a plastic rod and they acquire negative charge, and we have a glass rod, they acquire positive charge. When we then they comes together, they attract to each other because they are unlike charges. So this is the property of charge. And the experimental phenomena is when glass rods rubbed with wool or silk they repel to each other. So I hope this is clear. These observations lead scientists to conclude that there are two types of charges. Electrified bodies acquire electric charge through rubbing, and like charges repel, while unlike charges attract to each other. This is important property. Like charges repel to each other, while unlike charges attract to each other. This distinguishing property is called charge polarity. Clear? When rubbed objects are brought into contact, they lose their charges and no longer attract or repel other objects. This indicates that unlike charges neutralize each other. What is the meaning? Unlike charges, suppose we have a positive charge and we have a negative charge. When they are comes together, they are neutralized. So this indicates that unlike charges neutralize each other. Benjamin Franklin named these charges positive charge, or we can say positive and negative charge. So two type of charges, positive charge and negative charge. Positive means like charges, negative means like charges, positive negative unlike charges, negative positive, this is also unlike charges. By convention, the charge on glass rod or cat's fur is positive, while that on plastic rod or silk is negative. The gold leaf electroscope detects charges. So, gold leaf electroscope is an instrument that detects charges through the divergence of its gold leaves. When a charged object touches its metal knob, the divergence degree indicates the charge amount. Look at here. This is the setup of the gold leaf electroscope. What is electroscope? It is a device which is used to detect the charge. Materials contain balanced charges in their natural state. If a material having their natural state, they are balanced, composed of atoms and molecules. Electric forces are fundamental in nature, governing molecular bonds, solid structure, adhesion and surface tension. When a body is charged, it refers to excess or deficit of electrons. Yes or no? Suppose we have a body and they have excess amount of charge. So we can say the amount of charge is deficit. In solids, electrons transfer between bodies during charging. Rubbing a glass rod with silk transfer electrons from rod to silk, making the rod positive and silk negative without creating new charges. So this is the fundamental things or properties of the charges. Conductors and insulators. So here question arises, what is conductors and what is insulators? Let's see. Substances can be classified based on their ability to allow electricity to pass through them. Conductors readily allows to passage of electricity due to presence of comparatively free electric charges, and that free electric charges are electrons that can move within the material. Metals, human and animals bodies and earth are examples of conductors. So what is conductors? Conductors is a material that allow to passage of electricity due to presence of comparatively free electric charge that can move within the material. And what is the examples? Metals, human and animal bodies and earth also are the examples of conductors. On the contrary, most known metals like glass, porcelain, plastic, nylon and wood are insulators that offer high resistance to electrical passes. When charge is transferred to a conductor, you know what is conductor? It distributes across its entire surface, while charge placed on an insulator remains localized at the same spot. This explains why a nylon or plastic comb becomes electrified when combing dry hair or rubbing. But metals articles like spoons do not show this effect. It means if we transferred charges to any conductors, the charges are distributed across entire surface. And if we transfer it, or we can say if we transfer it charge on insulator, it localized, not distribute. It localized at same spot, because insulator cannot conduct electricity. The charges on metal leak through our body to, to, to the ground, since both are conductors. However, a metal rod with a wooden or plastic handle shows signs of charging when rubbed without touching its metal. I hope this is clear. So, this is the basic difference between conductors and insulators and their examples. Now, basic properties of electric charge. There exist two types of charges in nature. First one is positive charge and second one is negative charge, which have the tendency to cancel out each other's effects. So, when dealing with charged bodies that are significantly smaller in size compared to the distances separating them, we consider them as a point charges. What is the meaning? Meaning is that suppose we have a charge, two charge Q1 and Q2, and the size of the charges is significantly small as compared to distance between them, distance between the charges. So in that case, we called charges are point charges. In such cases, the entire charge of the body is treated as being concentrated at single point in a space. This simplification helps in analyzing electrical interactions between charged objects when their physical dimensions are negligible relative to their separation distances. Next property is charges hold some basic properties such as additivity of charges. We can add charge easily. Conservation of charge. Quantization of charge. So, all are the very important. Additivity of charge, conservation of charge, and quantization of charge. This is the basic property of electric charge. I hope this is clear. So, first is additivity of charges. Additivity means we can add charges. Addition. Suppose in a system we have 2-point charges Q1 and Q2. The total charge is found by algebraically adding Q1 and Q2, demonstrating that charges add like real numbers or scalars. It means what? It means we can add charge algebraically. Suppose we have a two charges Q1 and Q2, then what is the total charge? Q1 plus Q2. Clear? Or we can say we can add charge like a mass. For a system with n charges, suppose we have a n charges Q1, Q2, Q3 and Qn. The total charge is equals to Q1 plus Q2 plus Q3 plus Qn. So what is the meaning? Meaning is that we can add charges algebraically. So look at here. We can add all the charges algebraically, Q1 plus Q2 plus Q3 plus Qn, because we have a n charges in a system. Charge, like mass, has magnitude but no direction. Charge is a scalar quantity. It has only magnitude, no direction. However, unlike mass, which is always positive, charge can be either positive or negative. When adding charges in a system, this is important. when adding charges in a system, proper signs must be considered. For instance, in a system with 5 charges, plus 1, plus 2, minus 3, plus 4, and minus 5 in arbitrary units. Look at here. Here, two charges are negative, minus 3 and minus 5. Then the total charge calculation is plus 1, plus 2, plus minus 3, plus 4, and plus minus 5. When we add all these charges, you will be get minus 1 in the same unit, because we can add charge algebraically. Let us take another example. Suppose we have a two charges, plus 4 and minus 3. Then what will be the total charge? Is plus 1, because charges are, we can add charges algebraically, like mass, like any numbers. I hope this is clear. Additivity of charges. Conservation of charge. When bodies are charged by rubbing, electrons transfer from one body to another without creating or destroying new charges. This electron transfer demonstrates charge conservation, where what one body gains in charge, to other losses. In an isolated system with multiple charge bodies, interactions may redistribute charges, but the total system charge remains conserved, as verified experimentally. So, conservation of charge applies even when charged particles are created or destroyed within an isolated system. Natural processes can create charged particles, such as when a neutron transforms into a proton and an electron. These newly created particles carried equal but opposite charges, maintaining zero net charge before and after transformation. It means we can, in a single line, we can say, according to conservation of charge, charge neither be created nor be destroyed, only transferred one form to other form. So this is the conservation of charge. Quantization of charge. The fundamental principle of charge quantization states that all free charges are integral multiples of a basic unit charge, and that is E, expressed as a Q is equal to Ne. This is very important. Q is equal to Ne, where N is any integer or positive or negative. Electrons carry minus E charge, while protons carry plus E charge. And what is the value of E? Numerical value of E? The quantization of charge, first suggested by Faraday's electrolysis laws and demonstrated by Millikan's in 1912, indicates that charge exists in discrete units. It means charges exist in a discrete numbers. In SI units, charge is measured in coulombs. This is the unit of the charge, coulombs, represented by C, where the numerical value is E is equal to 1.6 into 10 raised to the power minus 19 coulomb, which is approximately 6 into 10 raised to the power 18 electrons constitute 1C. Smaller units like microcoulomb means 10 raised to the power minus 6 coulomb, and millicoulomb 10 raised to the power minus 3 coulomb are commonly used in electrostatics. So all are important. So in simple terms, we can say charges are equal to Ne, or we can say in a fixed amount, or we can say integral multiple of E. For a body containing N1 electrons and N2 protons, listen carefully, a body containing N1 electrons and N2 protons, the total charge is N2 into E plus N1 into minus E, which is equal to N2 minus N1 into E. So this is the total charge. And the charge can only change in steps of E, though this discreteness becomes imperceptible at macroscopic scales dealing with charges of few microcoulomb. This is analogous to how closely spaced points appear as continuous line from a distance. So here the important point is this one, Q is equal to Ne. And a 1 microcoulomb charge contains approximately 10 raised to the power 13 electronic charges, making the quantization negligible at macroscopic scales. However, at microscopic levels involving few hundred electronic charges, the discrete nature becomes significant. So this is the quantization of charge. I hope this is clear. Example: if 10 raised to the power 9 electrons moves out of a body to another body every second, how much time is required to get a total charge of 1 coulomb on the other body? So here we have to find out the time. Solution: in 1 second, 10 raised to the power 9 electrons move out of the body according to question. Therefore, the charge given out in 1 second is 1.6 into 10 raised to the power minus 19 into 10 raised to the power 9 coulomb per second, which is equal to 1.6 into 10 raised to the power minus 10 coulomb per second. The time required to accumulate of a charge of 1 coulomb can then be estimated to be 1 coulomb per second divided by 1.6 into 10 raised to the power minus 6 coulomb per second. So calculating this, you will be get 6.25 into 10 raised to the power 9 second. So in another units, it will be 198 years. Thus, to collect a charge of a 1 coulomb from a body from which 10 raised to the power 9 electrons move out every second, we will need approximately 200 years. 1 coulomb is therefore a very large unit for many practical purposes. It is, however, also important to know what is roughly the number of electrons contained in a piece of 1 cubic centimeter of a material. A cubic piece of copper of side 1 centimeter contains about 2.5 into 2 raised to 10 raised to the power 24 electrons. This is a very big number. Clear? Coulomb's law. This is important. So this is geometry, and in figure A represent geometry and figure B forces between charges. Coulomb's law quantifies the force between 2-point charges. Look at here. We have a 2-point charges Q1 and Q2. Coulomb's law tells us about how much the force between these charges. When their linear size is much smaller than the separation distance. So their linear charges means size of charges are much smaller than as compared to their distance, and the distance is this one. Coulombs find that the force varied inversely with distance squared and directly proportional to charges magnitudes. and acted along the line joining them. For charges q1 and q2 separated by distance r in vacuum. So in that case, F is equal to K mod of Q1 Q2 divided by R square. This is the mathematical form of Coulomb's law. Let's see. Suppose we have a two charges Q1 and Q2, and the distance from the origin is R1 and R2. So according to Coulomb's law, the force between these two charges are inversely proportional to squared distance. F is inversely proportional to square of distance and directly proportional to mode of, or we can say magnitude of, the charges, that is q1 and q2. And to removing the proportionality sign, there is a constant, that is k. So the formula become F is equal to k q1 q2 divided by r square. So this is the mathematical form of Coulomb's law. Now the force F12 means what? F12 means force exerted on charge first due to second. F12 means this. And F21 means force exerted on charge second due to first. And the distance is R2 minus R1. R2 from the origin, R2 is having large distance. So this is the displacement. And here Q1 and Q2 both are positive. So like charges are repelled to each other. So direction of Q1 is along left side and direction of Q2 along right side. Similarly, suppose we have a two charge Q1 and Q2, and the magnitude, the product of Q1 Q2 is greater than 0. It means what? It means Q1 is positive and Q2 is also positive. So they are like charges, so they repel. And so another case, Q1 and Q2, the product is less than 0. It means one of the positive and one of these negative. It means suppose Q1 is positive, Q2 is negative. Q1 is negative and Q2 is positive. Both cases are happens. So the force exerted on charge Q1 due to Q2 is F12 and the direction is along Q2 because they are unlike charges. Coulomb used a torsion balance to measure force between charged metallic spheres. He discovered the law by dividing charge q between identical spheres to get q by 2 each. Measuring force at different distances for fixed charges. Comparing forces for different charge pairs at various distances. The constant k determines charge unit. In SI units, k is equal to this one. For q1 is equal to q2 and that is 1 coulomb at r equal to 1 meter, what will be the F? F is equal to 9 into 10 raised to the power 9 Newton. K is usually written as 1 upon 4 pi epsilon naught, where epsilon naught is vacuum permittivity. And the value of vacuum permittivity is 8.854 into 10 raised to the power minus 12 coulomb square per Newton per meter square. All these units are very important. K, unit of charge coulomb, and epsilon naught, or we can say vacuum permittivity. So this is the geometry and forces between charges. Vector form of Coulomb's law between charges at R1 and R2. First this FQ1 at R1 and Q2 R2. So R21 is equal to R2 minus R1, the distance between these two charges. And R12 is equal to R1 minus R2 is equal to minus R21. And unit vectors. R21, this one. How we can represent? Vector R21 divided by their magnitude R21. Similarly, R cap 12, this is also unit vector which represents the direction. So R12, this is the vector, and R12 their magnitude. And R21 is equal to minus R12. A complete vector form, this one. F21 is equal to 1 upon 4 pi epsilon naught Q1 Q2 divided by R21 square R cap 21. Key points. Works for both like and unlike charges. It means Coulomb's law works for both like charges and unlike charges. Follows Newton's third law, and that is F12 is equal to minus F21. Every action is equal and opposite reaction. Here, the magnitude of force, or we can say force on charge first due to second, the magnitude of force and the force acted on charge first due to second is equal to magnitude of force acting on charge second due to first is equal, but their directions are opposite. Look at here, the directions are opposite, so negative sign represents only direction in the vector form, and valid for charges in vacuum. So this is important points. Example, Coulomb's law for electrostatic force between 2-point charges and Newton's law for gravitational force between two stationary point masses. Both have inverse square dependence on the distance between the charges and masses respectively. A is compare the strength of these forces by determining the ratio of their magnitudes. First given is for an electron and proton. Second is for two protons. B is estimate the accelerations of electrons and proton due to the electrical force of their mutual attraction when they are 1 angstrom. 1 angstrom means 10 raised to the power 10 meter apart. And given terms is mass of proton is this one and mass of electron is this one. So first is the electric force between an electron and proton at a distance r apart is Fe is equal to 1 upon 4 pi epsilon naught E square divided by R square with negative sign. So this is the electric force between electron and proton, where the negative sign indicates the force is attractive. The corresponding gravitational force, always attractive, is this one. Fg is equal to minus G mp me divided by R square, where mp is and me are the masses of proton and an electron respectively. Mass of proton and mass of electron. So that their ratio, the magnitude ratio is E square divided by 4 pi epsilon naught G mp me is equal to 2.4 into 10 raised to the power 39. Second is, on similar lines, the ratio of magnitudes of electric force to the gravitational force between two protons at a distance r apart is this one. E square divided by 4 pi epsilon naught G mp is equal to 1.3 into 10 raised to the power 36. However, it may be mentioned here that the signs of the two forces are different. For two protons, the gravitational force is attractive in nature and the Coulomb's force is repulsive. The actual values of these forces between two protons inside a nucleus, distance between two protons approximately is 10 raised to the power minus 15 meter inside a nucleus, are Fe is equal to 230 Newton, whereas Fg is equal to 1.9 into 10 raised to the power minus 34 Newton. The ratio of the two forces shows that electrical forces are enormously stronger than the gravitational forces. Second is the electric force F exerted by a proton on an electron is same in magnitude to the force exerted by an electron on a proton. However, the masses of an electron and proton are different. Thus, the magnitude of force is this one. 1 upon 4 pi epsilon naught E square divided by R square is equal to this and this. When we solving this, we get 2.3 into 10 raised to the power minus 8 Newton. Using Newton's second law of motion, F is equal to ma, the acceleration that an electron will undergo is A is equal to 2.3 into 10 raised to the power minus 8 Newton divided by 9.11 into 10 raised to the power minus 31 kg is equal to 2.5 into 10 raised to the power 22 meter per second square. Comparing this with the value of acceleration due to gravity, we can conclude that the effect of gravitational field is negligible on the motion of electron and it undergoes very large accelerations under the action of Coulomb's force due to a proton. The value of acceleration of proton is this one, 1.4 into 10 raised to the power 19 meter per second square. Thank you for your attention.